guys, welcome back to Nicktronics, and as you can see, work has begun on LEGO Defender version 2.0. I have successfully built the painful part this time in the base of the Defender, and I figured I would start off this video about 2.0 explaining some of the upcoming changes of how I'm going to address the laundry list of things that I said was my future self's problem in my last video. Because my future self in my last video is now my present self. So let's get into it. So while Rev 1, or I think I left this as 1.5 in my last video, was very great, I figured I would refresh you all on the things that needed to be updated moving on into version 2.0. The first of which, as you can see here, is just the fact that it is very tethered. Power-wise, I did not have a mobile power solution, i.e. there was nothing battery powered. And this was going to be kind of difficult because not only does the Kria require 12 volts and I think up to 4 amps in transient modes, because I think this is a 4 amp capacity, or 3 amp capacity. So I need 12 volt, 3 amp power supply for the Kria. The motor I ended up using for the drive shaft was also 12 volts. And when I started looking around at 12 volt batteries, there's not really a lot of available solutions for 12 volts at this current capacity that are lightweight. Just the weight of having only the Kria on the robot here is already causing the suspension to squat. And when you compare it to our non-loaded Defender over here, I'm already peaking my suspension's capacity here with just the Kria on it. So adding a giant 12 volt battery just wasn't gonna happen. So that was issue 1. Second issue was the entirety of the LEGO construction with my bigger motor for the drive shaft. It was causing all of the Legos in the frame of the whole LEGO robot to flex. And this, every once in a while, this would cause the belt of the drive shaft to slip off. So that was just an inherent design flaw that required a full rebuild no matter what I did, which is why I didn't have the heart to do it in the meantime, and I just gotta rolled on to get the initial obstacle avoidance algorithm working on this. So as you can see, that's why we have a full rebuild for version 2. And I wanted to go back to the weight problem real quick before I get into the V2. Going back to, I think I mentioned it in either the blog post or in the video, talking about needing to find a lighter weight webcam. But just to further demonstrate like how much weight is ending up on version 1.0, I want to put everything together and then let's do a side-by-side showing you how much this is already weighted down with no power supply of any form on board yet, just the Kria, the drive motor, and the webcam. So let me shift these around real quick and I'll let you see a side-by-side. But as you can see, I don't have a whole lot of weight capacity left in 1.0. There's no power supply on here yet, and obviously we're pretty much loaded at this point. All right, so let's get into what is different about V2. As you can see, I've got all of my components laid out here to give the overview of it, because while the LEGO build is done, we've still got some development to do. So I'm embarrassed to admit this, but I didn't need to re-engineer an entire method of being able to add an electric motor to the LEGO kit itself. Somebody had already done it. Somehow I completely missed the conversion kits that exist for this specific LEGO kit for the Defender. I don't know how I spent so much time Googling this, and about a week after I finished this build, my Amazon account was just like, hey, are you interested in this cool little build out kit that includes LEGO motors for this with a whole new build guide of how to rebuild it with it? So bought it immediately, and here we are. I'll insert some pictures of what the motors look like here from the alternative build guide that comes with, because the kit's actually really cool. It comes with 3 motors, 2 drive motors, and a steering motor, kind of similar to my original design, but it takes out the entire gearbox and all that stuff, since you don't really need to have the mechanical gear shift, since you can just modulate the waveform to the electric motors, and that's how you shift. But yeah, and I was also pleasantly surprised that the motors and the little motor controller box are all powered in the kit. It comes with a little 3.7 volt lithium ion battery, so very small, very compact. I'll flip them around here and you can see, you probably already noticed that I have the back seat taken out there, but that's just, the battery and everything is contained in, so there's my 2 drive motors connected and my steering motor. So it's all contained in this nice little block. I also gained a little bit of weight threshold because now without the entire gearbox and most of the transmission, I gained some weight back, or gained some weight capacity back, and that took over. So that was a great solution. Wish I'd found it the first go around, but is it really a project if you don't do it the hard way for no reason the first time? It's not a Knittronics project if you don't. Anyway, so that little motor controller box actually has a Bluetooth receiver in it that you can control either by this remote, or there is an app, an iOS or Android app. So one of the first things we need to do is I have my Kria here, have a Bluetooth dongle for it that we'll use with the Ubuntu image on the Kria, and we need to do some Bluetooth hacking to figure out the commands to send this guy so the Kria can control the steering and drive remote or wirelessly, which segues into the next biggest change in Rev 2 is now the Kria is no longer mechanically tied to the actual robot. The Kria can actually be located anywhere as long as it is A, within Bluetooth distance, and B, is on the same local area network or the same Wi-Fi network, which leads me to update number 2, which is the camera solution. So with the Open CV library that Edge Impulse uses to access a video feed, you can either access a USB webcam in the device folder in Linux, or you can pass it an RTSP feed, which, after much searching on Amazon, I found a security camera that once you create a little account with Tapo, to get the security camera connected to your wireless network, it will give you a RTSP link that you can then plug into the OpenCV driver for Edge Impulse to then pull the feed wirelessly from this guy instead of wired here. Another bonus of why I chose this particular camera, which I'll just go ahead and open it, is that it only requires 9 volts, and I think the current capacity is also pretty low, which is 9 volts, 0.6 amps. So I'm gonna see how this guy does with start with a 9 volt battery and just see how we go from there. But this guy's also much lighter than this guy. So there we go. Definitely not gonna stick him on the hood like that I'm probably gonna figure out how to get him inside here, which means taking off this base or something, but we'll get there. That's ultimately the solution for that. So now that I've kind of given a high-level overview of all the different upgrades of what we're doing in Rev 2, the main 2 things on our checklist now are We need to figure out the Bluetooth so we can create a script on the Kria to control it remotely. And then I need to get the Wi-Fi camera set up so that I have an RTSP feed for the Kria as well. But those are the two main things. Let's get started with the Bluetooth. And what I'm gonna do for that is I've got the Bluetooth app on my phone. I downloaded the extra Xcode developer tools for my Mac, which means that comes with a version of basically Wireshark for Bluetooth. So we are going to put a trace log on my phone, send a bunch of Bluetooth commands to this guy for going forward, backward, turning, all that, and reverse engineer it from there. And that way we can transfer to the Kria. Let's get into that. Real quick before we get into the Bluetooth hacking, I figured I'd show you just how nifty and streamlined this conversion solution was compared to how long I spent painfully with this guy. So we'll take a look at the controller. So simply backward, forward, and then it also solved my steering problem of needing to know, it automatically stops when it reaches the full, because the encoder is already all programmed into the motor controller box, so that's just another thing off my to-do list. So yeah, really wish I'd found this last year, because it totally existed last year. Anyway, I've wallowed in that sorrow long enough. Let's actually do the Bluetooth hacking. So it looks like there's a couple ways I can do this. So I've got the profile installed. I rebooted my phone. So I've got Packet Logger open on my computer. Okay, so Packet Logger, I'm gonna do File, New, iOS Trace. And there we go. So it's recording my Bluetooth packets. So now I'm going to open the app, and we've got the XC2 controller board remote. So now I just need to turn on the motor controller in here. So it looks like I got a solid green light. So I think I should be connected. So let's try to move. So there's forward, backward. Looks like we're catching all that. And then I turn right, left. Oh, it looks like it's reversed. So I'm letting my trace run here. I'm just trying to make sure I gather enough data. Let's stop this trace and take a look at it. Let's make this easier. I'm gonna pull some of these commands out. Let's put them in an Excel spreadsheet, and then we'll take a look at it, because that'll be a lot easier to look at. Okay, so now that I did all my Bluetooth packet sniffing, I exported all of the commands into an Excel spreadsheet just so I could start trying to grasp what was going on better. It was pretty hard to see a pattern right off the bat in Packet Logger, but after doing some copying and pasting and using the magic of Excel to reorganize things, I kind of started to see a pattern. So I'm gonna talk you through kind of how I figured this out and what I ended up putting in my Python script that ultimately is going to control the Bluetooth motor controller from the Kria on the Lego Defender. So the first thing I did was I filtered out in Packet Logger. I filtered out, obviously I know the address since my computer has Bluetooth. There was other Bluetooth things happening. So the first thing I need to do is I only care about packets that were actually being sent to the Bluetooth motor controller in the Lego Defender. Then it was pretty obvious the handle was 004A, and I was, by reasoning, I'm only interested in the packets being sent to the Bluetooth motor controller. I didn't really see a whole lot coming back, and what I did see come back it just seemed to be ACKs that weren't doing a whole lot. But so I further filtered out in Packet Logger by ATT send type. The next field was the opcode field. So this is where this is kind of the first obstacle because there's a few different functions going on. There's the pairing with the actual device, so between my phone and the Bluetooth motor controller, that pairing process is going to send some commands, so there's going to be some unique opcodes for that versus just the actual functionality opcodes of like pressing a button. Although I did see it was pretty easy to filter out once I sorted by opcode. It was pretty easy to see that the only opcodes I really wanted to look at were hex 12. As far as the opcodes for the actual Bluetooth pairing process, I don't really need to recreate those packets from scratch because the Bluetooth drivers in Python are going to do all that for me, which I'll show you in the script I ended up making. So once I realized I wanted to look at opcode 12, I could see my attribute handle and the channel ID were all the same for all of those packets, so I could ignore that for now, and that left me at what the actual final data payload looked like for my target Bluetooth packets in question. So that I realized started with this 4A00 and then went through these, what is it, 1, 2, 3, 4, 5, 6, 7, 8 chunks of data here. So 16 bytes total. And for all of them, they were all the same here. So since it was the same for every button, forward, backward, left, right, I'm not gonna worry about picking apart exactly what these mean, because obviously I just need to send this exact same thing every time. So I'm gonna keep moving on, and that left me with looking at the final, let's see, 1, 2, 3, 4, 5, 6 bytes of the packet. So these final 6 bytes of the Bluetooth packet were what was changing every time when I would press a button, and would be somewhat relative to whatever button that was. So as you can see, I kind of started copying and pasting as much as I could and still didn't really see a whole lot. So I filtered, in Packet Logger, I was able to filter out specifically these particular packets, and a really nice thing is I was able to hit select all and copy paste. So the first thing I did was just copy them all into my Excel spreadsheet here. So this is just those last bits, or those last bytes of the data payload I was interested in. And first and foremost, I just wanted to see how many different unique packets I saw here, because in my mind, I really only should have had 4 different packet types, or I was assuming I'd only see 4 different unique data payloads, because I was thinking forward, backward, left, right, maybe a combination of the two, but it was kind of hard to, it wasn't really, I don't know. I figured 4, maybe the combinations that would make what, 8 unique ones max. However, upon sorting them, I noticed there were a whole lot of these 000001 CD commands. And basically, I noticed that whenever I was not pressing a button, or any brief moment that I was not pressing a button, the app on my phone, or this guy, is just continually sending this 00001 CD command, which immediately made me think that was probably the command to stop. And it looks like the app is just constantly telling the Bluetooth motor controller to just stop, 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 stay stopped. So that's my first clue. This was my final table where I broke everything out, and I noticed that because we're only looking at these last 6 bytes, my immediate idea was, I'm guessing the last byte's probably either a checksum, a CRC, something along those lines. But unfortunately, running those last 2 bytes through a CRC checker for any previous length of the Bluetooth packet, I couldn't find a consistent CRC for anything. So last byte, I eventually ruled out was not a CRC at all because it was always different. And it's not totally uncommon for Bluetooth interfaces to not have CRCs, especially maybe cheaper, more simplistic things like this. But what I did start noticing is, first of all, this byte 1 was always 0, 1. No matter what I did, it's always 0, 1. And that reminded me that in the app, I could connect to up to 3 devices at a time. So there were 3 different Bluetooth channels to connect to. So because I was connected to, I had my Bluetooth motor controller connected to channel 1 in the app, that told me this byte 1 was representative to device 1, channel 1. So 1 byte solved. But then I started noticing that between forward, I ran it a few more times and I would only do forward and reverse commands, and I noticed that when I would only do forward and reverse, bytes 2 and 3 here were always 0, but then I would see something in bytes 5 and 4. Furthermore, when I would drive forward, I started to see that forward always meant that byte 5 was 0, 1, and when I would go in reverse, byte 5 was always 0, 2, so we're good. And the same thing with left and right. I noticed that on byte 3, whenever I was going left or right, bytes 4 and 5 were always 0, and then byte 3 was always 0, 4 when I was turning right, and always 0, 8 when I was turning left. Which that just left me with byte 2 when I was turning left or right, and then byte 4 when I was going forward or backward. And then if I sent some sort of combination of, like, if I tried to do forward and turn right at the same time, I would see the same coordinating values, my forward value in bytes 4 and 5, and my turning values in bytes 3 and 2. However, I never quite figured out what specifically this byte 2 or byte 4 meant. At first I thought it was relative to the length I'd pressed the button, but no way I calculated it could I get it to come out to an answer that made sense, which then brought me back to this thing of, like, what the heck does byte 0 mean? And I saw a pattern eventually, let's say that, but to be honest, I still don't really know what it means. I just know that I eventually saw this pattern that for turning left and turning right, byte 0 was always hex 33 minus the value of byte 3, and then byte 2 subtracted, or that value subtracted from byte 2. Almost as its own form of type of a checksum. I thought it was the time that I'd press the button. However, when I wrote up my Bluetooth test script, I would try different values, and essentially the Bluetooth motor controller would just drive in that direction forever until I sent the stop command. Regardless of what value I sent in byte 2 or byte 4, it didn't care. The only thing it cared about is that byte 0 matched this little calculation that I found for that as its own little checksum. And as far as being able to see that, I don't know, I guess my engineering mathematics kicked in, and after staring at this for long enough in Excel, I kind of started to see that, oh yeah, you can always do this little equation here. And this equation is in hex, by the way. All of these values are in hexadecimal. But yeah, I know that may not be the most eloquent description. And if somebody is seeing what this actually means and is just pulling their hair out right now, please let me know in the comments. I would love to hear it. So with that, I was able to code up my little Bluetooth test script here. So using async IO and then the Bleak client in Python, I set my Bluetooth address here, the Bluetooth UUID, which again was another thing, I saw that in Packet Logger. My header was those first set of bytes that I noticed in the data payload never changed, regardless of which direction I told the motors to drive in. My module channel, like I mentioned, is 0, 1 out of 3. And then, I know, so like I said, port A and B, and port C and D, so the stop command was all zeros, and the checksum of that was CD. And then I did the same thing where forward, reverse, right, left, and then I came up with combinations of the two. As far as what I'm sending on bytes 2 and 4, I just put random values in there because, like I said, the actual value, no matter what I tried, didn't make a difference on the actual final result. The thing will drive in whatever direction until I send that stop command again. So in main, that's what I did is I went in, connect via Bluetooth to that UUID, and then I just sent it all of my different command options. We're gonna turn on the little motor controller box inside here. So flashing green light means that it's ready to pair. And we're gonna come over to, I've got on the Kria here, I've got my Bluetooth motor script loaded up. It's our lovely little Bluetooth dongle. So I'm going to execute that. Our green light is solid. Oh, rapid flashing. Woohoo, backwards, turn, turn. Let's see him actually do some driving. So I'll have to catch him after I hit go, but that's okay. So I'm just gonna run that same script again. Oop! Ah, he stopped just in time. Woohoo! All right, let's get the camera mounted. I got the security camera all set back up on the office Wi-Fi, so I went ahead and pulled up my old pumpkin stop Python script, which was my Python script that actually ran my Edge Impulse machine learning algorithm that would look for this pumpkin. This is my lovely little 3D printed Halloween jack-o'-lantern, and place a bounding box around him. And then I just added custom code to that part right after the bounding box has been drawn to say, hey, if there's a bounding box anywhere in the current image, stop. Otherwise, keep driving. So instead of being pointed to the webcam that I had plugged in via USB as the video source, I now have it pointed to my RTSP feed of my security camera that is now connected to the same network. So we've got the Lego Defender back up on its little safety workbench here. And I'm gonna go ahead and run, even though the camera's over here, I'm just gonna test it out. As soon as the 3D pumpkin comes into view, we should see this guy stop, so let's see what happens. We've got waiting Bluetooth connection, loading the Edge Impulse runner, selected the camera stream successfully. It's interesting, why does it think it sees? There we go. So I'm sitting here blaming my machine learning algorithm and decided to take a look and see what the stream looked like once I killed my Python script. That way I could actually see what my security cam app was seeing. And well, there's another pumpkin. pumpkin. I'm sorry, Edge Impulse. You did your job. You just have better attention to detail than I do. Okay. I'm short. I need the cameraman's help. All right. So now that there's only one pumpkin possible in the shot, let's try that again. We're doing some major mechanical repairs here. Come on. There we go. Having some major issues here. I came back at this and realized there was a whole plethora of issues, as is normal with most code. You don't just have one problem, you have many. First of all, the OpenCV library in Python is gonna be somewhat laggy. That was part of my issue. I also forgot about the fact that the Bluetooth library I'm using with Python is a blocking function, meaning that every time I send a Bluetooth command, it holds it blocks the rest of the program from executing, meaning I'm waiting for it to return. And since I was constantly sending Bluetooth commands, the constant stop command, because I assumed I needed to, since that's the way the remote worked, basically I was choking out the camera feed from the security camera with all of the constant Bluetooth commands. After some trial and error, I found the last command I send to the Bluetooth motor box that's what it'll do forever, which obviously I should have realized that when I was doing my initial testing, but sometimes when you actually start executing things, that's when things finally start connecting. Anyway, so I overhauled my code to set the buffer for the video capture in OpenCV2 to 0, because I don't want anything accumulating. I always just want the most recent frame, because this guy just can't move fast enough to really worry about dropped frames in between there. I also went into the settings of the security camera itself, because this guy can do up to 2K, and that was another big lag since this is going over Wi-Fi. I'm processing it in Python. 2K was just too much. So I set this down to 720p and chose the lower resolution stream, because this guy has a setting where he has two streams, the higher resolution and lower resolution. So set this to a lower resolution, still very usable. 720p is very usable for this particular application. And then I also changed my logic to only send a Bluetooth command when a change of direction or motion was necessary. For example, in my first test script where I just either drive or stop if I see the pumpkin, I really wanted to whittle this down to I only send a Bluetooth command when the pumpkin becomes present in the frame or is removed from the frame. I don't need to constantly lag it down with all these blocking functions of sending Bluetooth commands. So, and then the same with the obstacle avoidance. I only send a Bluetooth command when I need to steer in a different direction. I got my lag down pretty low. It started off around like the 30 to 40 second mark, and when I was constantly sending Bluetooth commands, and then it would also vary and it would get worse as the script would run longer. And then I'd eventually get buffer errors and all kinds of weird things. But now that I've got it whittled down, the delays about 1 to 2 seconds. Sometimes it'll float up to a few seconds, but definitely usable for this guy, and something to think about for Rev 3. I might just need to change all of my Python code to C++ and move it all into Vitus, but that's a very big future Whitney issue, so that's not today's issue. Let's take a look and see how this is going now. Oh, another thing I forgot to mention, I've changed the setup since I was last filming. I don't know why I didn't do this earlier, because the classify image demo script from Edge Impulse lets you see a little demo if you're running straight off of your device. So Now instead of my monitor being hooked up to my Remain laptop, I've got the Kria hooked up such that I'm just dealing straight with it. I'm going straight to the Ubuntu desktop image that's running on the Kria. So now we get to see a cool little demo of what the Defender's actually seeing, which is much more helpful than the print statements I was using when I was only connecting via the UART terminal. Should have done this a lot sooner. So let's take a look here. And so the lag, as you can see, we got it down pretty well. Thankfully, this guy doesn't have a whole lot of speed behind him to make sure. Wonder if that's enough to. So yeah, the delay kind of floats around here and there, but like I said, that's just a symptom of there's only so fast I'm gonna be able to run OpenCV in Python. All right, so now that we tested the basic stop-start script, let's see what the full obstacle avoidance script looks like with our actual steering. So hopefully with the lag down as much as probably possible at this point, it'll be somewhat workable. We'll fire it up here. And off we go. Oh, there it goes, finally. Finally? So I'm learning you just can't send it too many Bluetooth commands back to back or it spazzes it. Ah, there we go. Ha! Finally. It works. It works. Finally got it to work. I'm afraid to touch it now.